this video, we will cover data preparation, which is about cleaning and reshaping data so it can become more useful to us. Data analysts will often call data preparation activities as data munging or data wrangling because at times it almost feels like wrestling with data to get it in a form and a shape that we can use to extract insights or to make it amenable for further analysis or as an input into building predictive models. The reason we have to spend time and effort preparing data is because the data we often have is rarely collected with a view to supporting analytics. It is mostly intended to support transaction processing or managing operations, or gets generated as a side effect of a business as usual process. This last piece, by the way, sometimes is called digital exhaust. Very often, data is dirty, which means data can be missing or duplicated or in the wrong format, lie in different data sources or files, have character set issues that may arise from differences between Unix and Windows, etc. Sometimes data needs to be cleaned up with additional mappings or filtered for items of interest to us, and so on. Data analysts, they spend a great deal of time cleaning and preparing data for analysis. In fact, nearly 80% of analytical effort is expended on data preparation, cleaning, and such operations. Traditionally, this data cleaning work has been referred to as ETL processes, with ETL standing for extract, transfer, and load. Nowadays, data engineers and data scientists will set up defined data pipelines, which would be a series of data processing steps that ingest and bring data to a desired format and shape. In this video, we will cover some of the common data preparation operations and talk about what each of them does and how they are useful. This will then be followed by a separate video that will cover these operations in Python. But for now, let's just try to get a conceptual understanding of the common operations on data that we often have to perform. So with that, let's switch to the slides. These are the basic data operations that we will be covering today. And let us move to the next slide. Let's start with the diamonds data set again. Remember, this is a data set of about 50,000 diamonds. And for each diamond, we know several key attributes. We know the cut, color, clarity, the depth, the price, the caratage, etc. And all of this information is there in this data set. One of the most common operations we have to perform is we have to select columns. These would be columns of interest to us. And the reason we have to select a subset of all of the columns available to us is because sometimes there might be hundreds of columns, if not thousands, that are available. Many of these columns, also called features, they may be redundant or they may be unrelated to what we are looking to do with the data. And sometimes many of the columns may just be blank or may not contain enough information to be of practical use to us. Selecting columns is a very straightforward operation in just about every analytical software you would run into. So here, for example, for our diamonds data set, here is a subset of the data with just 3 columns selected: carat, price, and color. This is fairly straightforward. Similarly, if you remember the cars data set, which had a number of attributes for several models of cars in the 1970s, here is a subset of that with just the miles per gallon, number of cylinders, displacement or engine size, horsepower, and weight selected. So this is reasonably straightforward. Selecting rows, however, can get a little more complex and involved. This is often known as querying data or filtering. And here you have to specify conditions for different rows that must be satisfied before the row is returned in your query. So to the right, you see a subset of our diamonds data set here with certain conditions applied. We were looking for data where the caratage was greater than 3 and the cut was equal to premium. This query returns us the 13 diamonds out of our 50,000 diamonds that meet these two conditions. Queries can be made arbitrarily complex, and they are a very powerful way to identify specific observations that we have an interest in. Next, before we move on to additional data operations, let's just talk for a little bit about data types. A data type is an internal representation of how analytical software treats and manipulates data. Most modern software libraries, they generally have sufficient intelligence in that they will auto detect and manage data types by themselves. But sometimes you may need to intervene and make sure that your data is being dealt with correctly by the software. Here are the different data types that are available in Python, especially when you're using the pandas library. And similar constructs exist with other software as well. So you have Boolean, which is when a value can take either true or false values. And true and false here does not mean the text true or false. This is something that has a specific internal connotation that the software can use. Similarly, you have categories, which means that the data you have in a particular field is not a number, but categories. Say, for example, species, names of countries, names of people, and such. You also have floats and integers. These are different types of numbers. And date time is yet another data type that is often used, which essentially is an internal representation of date or time variables. Very often, we find that dates are expressed as text or strings, and they may have to be converted into date time so that the software has awareness of the fact that the characters or the phrases that appear, they are dates and not strings or texts. So consider the empty cars data set. Now, if you look at some of these columns, say for example, let's look at cylinders. We find that there are three types of cylinders. There are 4-cylinder cars, 6-cylinder cars, and 8-cylinder cars. In some ways, cylinder, even though it appears here as a number, is not really a number. It is really a type of a car. It's a category because you are never going to have a car with 5.5 cylinders, for example. You can convert them into discrete categories, and then the software will treat them as if they were categories as opposed to numbers. These conversions are fairly easy to perform, whether using Python or any other software. Adding and deleting columns. So sometimes you may need to add a column to a data using some calculation. So here, let's take an example. We have our diamonds data set all the way up to here. And what we wanted to do was we want to calculate the z-score or the normalized value for carrots to the right of this data set. This is something we can quite easily do. We can specify a formula for how this should be calculated. Now, we will be looking at normalization and z-scores and such stuff in a subsequent video. But for the moment, remember that normalization or standardization or calculation of the z-score here is nothing but taking the carrots, taking their average. From every observation, you subtract the mean and divide by standard deviation to get this particular value. And that is what we have been able to do. We can add different types of columns, which include text operations, which combine several other columns, and so on. So there is a wide range of possibilities to add columns to your data set. This comes in handy when you're doing feature engineering, which means you are trying to do something to build up your feature set for additional analysis. Sometimes you may need to remove columns to remove unwanted information. Again, that is also very straightforward. If there are columns that you believe are not useful to your analysis and you want to deal with a lighter data set, you can absolutely do so. That is generally very easy to do. And very often, as part of the initial data cleanup, that is a step that is performed to get rid of irrelevant or redundant columns. Reordering columns refers to changing the order in which your data columns appear. So in this situation, maybe we want to see price first. And it's quite easy for us to do that. We can specify the order in which these columns appear, and we can make price to be the first column if that is what we choose to do. Sorting values in a data set is a very common task. And again, nearly all software offers that as a functionality. Those who use Excel, we always find ourselves sorting data to find out the largest values or the smallest values or sort things in alphabetical order. Uh, Here we have an example of sorting the diamonds data set by carat, price, and depth in that order. So first, look at the carats and sort it in descending order, showing the heaviest diamonds on the top. If the caratage is equal, then sort by price, which should be the next order of sorting, and finally by depth. So this is the result of such sorting. And look at these two diamonds here, and you will notice that they have the same price and they have the same weight in terms of carats, but they differ in depth. And because we sorted by depth in descending order, the one with the depth equal to 62.5 appeared first before the diamond with uh, depth equal to 61. So fairly straightforward, not much more to say. Renaming columns is again very often needed to simplify column names, for example. Very often, when you get data from systems of record, you will find that they contain underscores or are generally very long, and you may want to simplify their names and or make them just more concise. So, for example, in this particular example here, we renamed price to dollars and we renamed carats to weight. Uh, but again, we can give our columns any names that we like. Very often, our data will have duplicate information. So you may need to drop any duplicate rows that exist in your data in order to clean it up. And in fact, you can also limit the duplication to a subset of the columns. And what does that mean? Let's have a look at an example. Let's look at this fake artificial data set we just created at random. And this has three columns. It has a column for state. We have a column for two variables, and we just call them variable one and variable two, though they could have been just about anything else. If you look at these two rows, you find that they are identical in every respect, and they're just complete copies of each other. If we were to drop duplicates in this data set, one of these will be removed, and it will not matter whether we remove this one or whether we remove this one. But when you look at these two rows, we find that they are not identical because these values here are different between these two rows. If we were to look at duplication only from the perspective of state and variable 1, we find that they are actually duplicates of each other. And if we decide that we want to drop these on the basis of just these two columns, state and variable 1, then we will need to drop one of these two. We have to provide the logic so that the software will know whether to drop this one or to drop this one. Generally, it will keep the first one, that's the default in Python, and it will drop the second one. So if we were to look at how the drop to duplicate functionality will work in software, so this is an example of just dropping the duplicates based on all the columns. And we see that this last one, or maybe this one, because we can't make out one from the other, has been dropped, and we only now have these 5 rows here instead of the uh, sorry, we have the 6 rows here instead of the 7 that we had before. Now, when we look at the dropping of duplicates based on a subset of the columns, which means just state and variable 1, we find that this row has been retained whereas this one has been dropped. And that's what I mean when I say dropping duplicates by a subset of the columns. Very often, we need to replace values in data. So again, we'll take the same data set we had, and maybe what we desire to do is we want to replace uh, the state acronyms by the full names of the states. Very easy operation to do in just about every software, including in Python, and you see the results here. Sometimes we need to convert continuous variables into categories. And what that means is that based upon a numerical or a continuous value, we want to give plain English labels to our data. So, for example, consider this the same toy data set. We have three columns: state, variable one, variable two. And what we want to do is that based upon variable one, we want to give every row a particular name. So, for example, we want to say that if this is 2 or lower, call it small. If it is 2 to 4, call it medium. And if it is 4 to 6, like here, for example, call it large. We can quite easily do that. And here it is. We can insert a new column in our data set where we have labels that were determined by the values of this specific column here. So that is what binning means. Now, in this situation, we performed binning based upon our human judgment. And when we do such binning, what we often find is that some of our bins will have a lot of data and some others will have very little. And maybe that is what we desire, and that is completely fine. But sometimes we want bins or buckets that contain roughly equal amounts of data. We can do that by using quantiles as bins. So, in such cases, our intervals. So here, for example, we had intervals 2 to 4, and 4 to 6. We may not have equal intervals. Some intervals will be larger or some others would be smaller than the others. But the count of observations in each bin would be similar. And I can explain that much better with an example. So for our diamonds data set, if I were to say that look at the price of the diamond and categorize each observation as belonging to one of four categories: economy, affordable, pricey, and expensive, and do so in such a way that I don't want to tell you what the limits should be uh, for economy, affordable, what the thresholds should be, but determine it yourself based upon the quartiles. So take all the data in the first quartile and put it in economy. Take all the data from the first quartile to the second quartile and put it here. Take all the second quartile to third quartile and put it in the pricey bucket, and everything quartile 3 onwards to the max, put it in the fourth bucket, in the expensive bucket. We can easily do that, and these are the different quartiles that were used for such bucketing. So this is the minimum value of our diamonds. This is the maximum value. And these values here that you see are the different quartiles. And the count of diamonds in each bucket is roughly the same. And one thing I wanted to point out here was the interval notation that you might run into if you're looking at data from your software or something that may be shared with you by your data analyst. So let's get rid of some of the ink here so I can show you what this means. So you will see that the way these intervals are expressed is that some of them have these parentheses, and on the other side you have these square brackets. What this means is the parenthesis means the value next to the parenthesis is not included in the range, whereas the square bracket means that is included. Now, in this particular situation, The parenthesis always appears on the left and the square bracket on the right. But if you are using interval notation, it could actually, either of these could appear on either of the sides. So just wanted to point that out. Something to be aware as we look at data analysis. And here would be the result of such binning into quantiles. If we were to take the results of our binning and make it part of our data set, this is what it would look like. So for every diamond, I have this part here in yellow, the quartile information and the prices, and the category that I have created. So this is just an example. There is no limitation to what you can do with binning. You can use any column for binning. You can decide your own labels. You can decide your own thresholds. And you can also ask the system to build the thresholds for you. Another thing that we often have to do as part of data preparation is extensive text operations. A lot of our data comes to us in the form of text. Sometimes we have to take the text data, split it, combine certain types of text, and do many other things. To the right is a list of all of a number of data operations that are possible on text data in Python. And actually, what you see here is a screenshot from a book by Wes McKinney. And I'm not going to spend too much time here on this, but the key takeaway here is that you can do just about anything you can think of with text data. You can identify data that contains a particular piece of text. You can count the number of occurrences of a particular pattern. You can look for text that ends with something or starts with something. You can join, you can calculate the length, you can convert strings or text to uppercase or lowercase, and so on. So you can do a lot of work with text data. Next, I wanted to talk about joins. Now, very often our data doesn't appear neatly in just one single data set. Sometimes the data is spread across multiple files or multiple data sources, and it has to be brought together and combined using some reference field between the data to create a data set that is useful for us. This requires connecting two tables or two data sets based on some sort of a reference field. Those who have studied SQL will find it very easy to understand, but even if not, conceptually, the idea behind this is very straightforward. So you may have two data sets that share a common field. If you want to combine both of the data sets into one based upon that common reference field, you can do so in four ways. First, you could take the first data set to be the primary one and pull in all information from the other data source and leave out any rows that may appear in the second data set here that do not appear in the first one. And that is what is called a left join. You could easily reverse that process too. You could make this data set primary and pull in information from the left data set into your combined data set, ignoring anything that is just unique to this data set but does not appear in C. That is called a right join. You could also say, I'm only going to look at the intersection of both of these data sets. I'll just look at stuff that is common between the two. So I just want to look at the intersection of these two, and that is called an inner join. And you can take a more expansive view as well. You may say, let's just combine everything that appears in A and B and put it all together in a single data set. And that would be called an outer join. Let's look at an example because otherwise it stays too theoretical. So let's consider two very simple data sets. So for example, let's just call it DF the first one, and let's just call the second one as df underscore rent. And what that means is, so df stands for data frame, which is terminology I have borrowed from Python and R, but and also SAS. But similar constructs are there for just about any analytical software you would use. So here we have information on 5 individuals. And again, remember that there is no science behind any of this. This is all completely random data. We have 4 variables available for 5 people. And we also have a different data set that tells me for 3 American states what the average rent is in each state. What I want to know is, I want to know what is the average rent for the state that this person is living in, and I want to put this here on the right hand side. The way I bring this data here is through a join. If I were to do a left join, this is how I would do it. I'll take all of my rows from my data frame or my data set, the first one, which is df, and I'll put them all here, just like they appear first. And here, then, by combining it with the state field, which is the common field between the two, I will put in the average rent values here. And you will notice that I get a missing value, NaN. NaN stands for not a number in Python. Now, these graphics or screenshots were prepared using Python, so hence my bias towards Python. But all other software behave pretty much the same way. So that's because this person lives in New York and information for the rent in New York is not available here. And the same thing again here. This person also lives in New York and we don't have the data. Now imagine if we were to do a right join. Let's change the ink color so that I can write in a different thing. Now, what I do now is I take this data frame and I copy it as it is. So I take, and it's kind of spread out a little bit here. And then I populate all these other columns from the first one, right? So these 3 columns, I bring them in here. You will find that instead of 3 rows, I have 4 rows here. That's because there were 2 people that it found in California. So when it got to California, it found 2 values here, uh, and it provided me both of those here. So this is an example of a right join because I made this data set to be primary. Let's look at an inner join. An inner join, as I explained earlier, is really just an intersection of both of the data sets. Let me get rid of some of the ink. And if you look at the intersection of both of these, you will find that the only states that are common based upon our reference field state are California and Florida, and which is what we see here, Florida and California. California gets repeated because there are 2 people from California in this data set. When I do an outer join, it includes all of the rows here as well as here. When I look at the join, I find that I take all the rows that appear here as well as here, and I combine them into a single data set here. And you will see that this has more rows than either of the original data sets, and that's because it is a combination of both of them. And wherever it can't find any values, it puts a missing value, like so here, here, as well as here. And that's an example of an outer join. Sometimes we need to simply combine data sets without any fancy operations of the type that we just saw. So imagine you have 3 files. Every month you receive a new data file for sales or commissions or whatever else it is that you are tracking. And all you need to do is to just combine them together, just join them, just put one on top of the other so that you have a more complete data set. For doing something like that, you can do concatenation, and we will look at an example of concatenation here. So we have the same two data sets that we looked at before, and when we combine them, so we can stack them either one on top of the other, like here. So we put one on top of the other, and that's what we have done. And then everywhere where we don't have information, it just puts a missing value, which is understandable. And or we could put them side by side as well, which means we put them here, and then the other one comes to the right of that, and the blanks are identified as missing values. Next, we will deal with missing data. Missing data is a long topic, and this video is already quite long. So let us take a pause and come back to dealing with missing data in the next video.